8 in the Memphis room, actually. That is part of a bigger event. 6:30 tonight. Yeah. Okay. Sorry. Yeah, but if you say a half hour before, people come, and it's okay. Okay. So it's a rehearsal a bit for what will happen tonight in the Memphis room, which is part of a bigger event about what happens in terms of sea level rise, in terms of impacts on the low-lying areas, if we try to meet the requirement of the Paris Agreement, 1.5 and a little bit below, or if we overshoot these limits. So here, this presentation is about the basics of about projections of sea level rise. So actually, I really like starting from the beginning when I present that, and starting by what is climate change. Climate change is heat excess that we introduce in our system in terms of radiative balance. You know, the climate at different latitudes is determined by how much radiation we get and how much the heat transport is redistributed from the equator to the pole. And with our carbon emission, we have been introducing a heat excess. So our radiative balance is actually unbalanced right now. And most of the heat excess is really absorbed by the ocean. Most of it, 90% of it, absorbed by the ocean. So without the ocean right now, we wouldn't be able to really, let's say, be able to live in decent conditions outside. What is really important is that if we want to have the system balance again, okay, we have to remove 60 ppm of CO2 in the atmosphere. So this is how we want to meet the Paris Agreement, okay? 1.5 and below means go back to pre-industrial concentrations in terms of CO2 in the atmosphere. So it means removing about 60 ppm of CO2 in our atmosphere. Of course, one of the main impacts of climate change is global mean sea level rise, because we have been melting most of our terrestrial cryosphere. And global mean sea level rise right now has been about 20 centimeters in absolute number since the end of the 19th century. So 20 centimeters in vertical translates very differently for all territories, because some territories have very high cliff at coastline, but many territories are also low-lying areas that are already at sea level. So 20 centimeters in vertical translate in a lot of hundreds of meters or kilometers for some of those territories that are low-lying areas. Most of the sea level, I mean, there are two main contributors to global mean sea level rise. One is the ocean expansion. Okay, ocean thermal expansion is important. As I said, ocean absorbs 90% of the heat that we are introducing, heat excess that we introduce in our system, and the rest is due to cryosphere melting. And then there is a little part about underground storage of water as well. So ocean thermal expansion is very important to understand, because as any fluid, when it absorbs the heat, it just expands, okay, horizontally but also vertically. So for ocean expansion is quite important, and so far it was the main contributors until 2005, when the main contributors became the cryosphere melting, actually. The cryosphere has different contributors term, okay? Most of it is about glacier mountains melting, okay? And the rest is about Greenland melting and Antarctic melting. Not that Antarctica is not melting, is melting twice as less as Greenland, for example. In terms of projection, so this is what we have by the end of the 21st century. If we consider the low emission scenarios, that is about 2 degrees, okay, that's 2.6 scenarios, and the 8.5 scenarios, which is the worst case scenarios, okay? So in terms of low emission scenario, we reach about, let's say, half meter of sea level rise by the end of the centuries. And in the case of high emission scenarios, so we reach around 1 meter, let's say, a little bit less than 1 meter global mean sea level rise, okay? So we know that sea level rise is not homogeneous, okay? Here is global mean, but it means that in some places, because of oceanic circulations, atmospheric circulations, glacial isostatic adjustments, solid Earth vertical movements and horizontal movements, sea level rise can be higher or lower depending on where we are. So that's a global mean. Just keep that in mind, because when you try to make adaptation measures, actions on your territories, you have to adapt in function of how much sea level is planned to rise. Well, out of that, you can see that Greenland contributes very little by the end of the 21st century, a little bit more in the case of high-end member scenario. And Antarctica contributes more or less the same in the two different scenarios, but this is because Greenland and Antarctica is fairly different. Greenland is melting at the surface, while Antarctica is very seldom melting from the surface. It's melting from below. Then I explained that later on. The real impact of the cryosphere has to be seen on the longer term, so a few centuries. If we want to see the difference on the implementation of the two different scenarios, so the most low emission scenario or the high-end scenario, we have to look well beyond the 21st century. And this is because of physics of the ice. The ice is as the water. It absorbs the heat on a very, very long time scale. So right now, if you compare, for example, the same thing, the thermal expansion for the ocean, for the two scenarios, there is a little difference. And because of this very large heat capacity and very long thermal inertia, okay? So it's really important to project sea level rise well beyond the 21st century. This is why IPCC proposes projections in 2300 and even on a longer time scale. One very important aspect for Greenland, for example, but also for Antarctica at some point if it starts melting, is the climate memory of ice sheets, okay? So the ice, as the ocean, absorbs the heat on the very long time scale, okay? When it's very warm, it starts retreating, okay? Because of the heat it has been accumulating so far, and because of the heat it's accumulating at the moment. Then if we stop, for example, warming the system, okay, after several centuries, if we go back to a low CO2 concentration in the atmosphere, the ice sheet still retreats, okay, until the heat that they have absorbed so far is completely released in terms of melting, okay? So that's why we say, even if we stop warming our system right now, okay, the ice sheets will continue to melt and sea level will continue to rise anyway after several centuries. Okay, so that's very important because the more we warm now and the longer it will take for the ice sheet to really stop melting and equilibrate again. Okay, so this concept, okay, is built on the fact that the ice sheet have accumulated heat for several centuries to millennia. We are adding more heat right now, but the effects will be seen in the future, on the long-term future. So these conditions very much the discussion that we have if we want to understand on which pathway we want to project our future, actually. And so this is where the concept of sea level commitments comes, actually, okay? This depends very much on how fast and how much we mitigate our emission, okay? So we cannot avoid sea level rise right now, okay? So if you understood well, I mean, whatever is our future, we will have anyway some sea level rise. How much will depend how fast we mitigate and how much we mitigate our emission. So those are some few results, very recent results in the literature that illustrate a bit the concept of that. I mean, so there's a recent paper from Jason Box, okay, that shows you the Greenland projections in the red line plus the uncertainty in the case of high-end scenarios by the end of the 21st century. And then you see above this blue dotted line, okay, that represents the sea level commitments, the amount of sea level rise that we already have committed with the heat that we accumulated so far in the ice sheets. And you can see that it's well above the high-end emission scenarios, okay? This is because when we do projections with our ice sheet model, okay, we have to initialize the heat absorption in the ice sheet as well. But if we got it wrong, then the projection is wrong, okay? The blue line is based on observations and represents exactly the amount of sea level that we will get out of Greenland, even if we stay at the temperature as today for some time, okay? So this is already the sea level that we committed to right now, okay? And as you can see, the high-end member scenario is well below this blue dotted line, which means that our simulations have the wrong baseline to initialize the scenarios, okay? And if we prolong this blue dotted line up to 2300, okay, and you can see the projections for Greenland for 2300, you can see that we are in between the scenario of low emission and high end member scenario, okay? So it means that we have to redo our simulation correctly, properly. We are underestimating the sea level rise that will come out from Greenland. So this is a very recent paper that came out a few weeks ago. Jason will be there next week, I think, and he will explain that a bit better. But that shows you that this climate memory of the ice sheets is something complicating to take into account in the ice sheet models, but it's very important, especially if you get the baseline wrong for the projection. In case of Antarctica, that's different. We also have heat absorption. Of course, it's an ice sheet, so it works the same way of Greenland, but it's a bit more complicated because Antarctica rests on a topography that you can see on the right. That is mostly emerged, so above sea level, but most of the blue area, the light blue areas are below sea level. So most of the ice is not floating, it's resting on a bedrock that is below sea level. So it means it's highly vulnerable to ocean warming around. Antarctica is located at the South Pole, so it's not melting as much as Greenland and in the surface. So most of the melting from Antarctica comes from ocean warming right now. But in the future, if we definitely warm our climate as much more than it is today, we will have also some melting at the surface. So in all the areas that are in light blue on the right maps of the bedrock of Antarctica, all the areas are vulnerable. In Antarctica, then, when the ice flow and arrives to the ocean, it starts floating, okay, because the ice density is less than the water density, and it forms what we call floating platform, ice shelves, okay? But those ice shelves, because they're floating, they're vulnerable to ocean heat from below, okay? So Antarctica right now is very vulnerable to ocean warming coming from below those floating platforms. Those floating platforms have the role of maintaining most of the ice flow in place within the ice sheets, okay? And if those platforms thin, okay, and disintegrate because of ocean warming, then they breaks, and what we call the grounding line, which determines the area where the ice start floating from the ice that is grounding inland, okay, it disintegrates and the flow accelerates into the ocean and causes a very rapid sea level rise, okay? So the fact that Antarctica has many sectors that are vulnerable to ocean warming is very problematic because instability behavior are definitely more difficult to predict than a simple ice sheet melting because of climate warming, actually. So this makes Antarctica a very challenging place to really understand and predict. Another type of instability that also makes those floating platforms very vulnerable is when in the future we will also have surface melts above the ice shelf. So the water will infiltrate the crevasses that are at the surface of the ice shelf, and when winter comes, it will just enlarge the cracks because the water will freeze again, okay? And this will foster and amplify the instability caused by ocean warming from below, makes also most of the ice sheet to retreat and enhance the discharge into the ocean, and then produces a larger sea level rise in a smaller amount of time because it will become much more unstable. So those are the projections that are given for 2300, because the timing of those instability is nevertheless a few centuries. As for the long-term melting, okay, as we say, we need few centuries to really see the impact of each scenarios. That's the same for those instabilities. We know that this is not really science fiction because paleoclimate data shows us that those instability already happened. We have the really evidence on the ground, okay, and the timing of those instability is really exactly what our ice sheet models are giving to us, a few centuries, and the amplitude of sea level rise is also the same. If we look back at different paleo periods in the past, let's say mostly the amplitude of sea level rise is about 10 to 20 meters, okay, in when Antarctic sectors disintegrate like that because of instability. So we know that the projections here that are showing around 2 meters of sea level rise in case we stay around 3 degrees or above. If we go to the high-end scenarios, which is the graph below, and reach 15 meters, they are not science fiction at all. They are completely in the range of what paleoclimate data tell us. So that's really important point. It's really not, yeah, as I say, it's really not science fiction. It's really likely to happen. Well, we also have thought for a very long time that East Antarctica was very, very stable. But we know now from a new geological data that actually it's not the case. Many of the sectors of East Antarctica have been collapsing as well. So we now have the ground evidence of that. So we know that those sectors can also disintegrate, but we know less because they are more challenging places to study. They are more exposed to storm when we go to the campaign to retrieve the archive, etc. So they are more challenging to really retrieve. Most of the area that are also vulnerable have a multi-year sea ice in front of them, so it makes also a hard time for scientists to reach and to study. However, we have the evidence of the fact that even East Antarctica is vulnerable to climate change. Okay, so the main message about this is that the fact is that sea level rise is unavoidable. Even if we stop warming right now, sea level will rise anyway because of the heat that has been absorbed by the ice sheet so far. So for 2 or 3 centuries, even more, perhaps a millennia, the ice sheet will continue to melt. And if we stay at the temperature as today, it will cause a 2 to 3 meter sea level rise anyway. So that's a big data. So this means that we have to adapt. It's not something that we just have to think for the next future. We need to adapt anyway. And it's a multi-generational adaptation actions that we have to plan, because it's not today we plan for 20 centimeter sea level rise. No, we have to think about perhaps a century or two ahead, just to say, okay, we have to protect our coast for a multi-meter sea level rise, at least 2 to 3 meters. And I can give you an example, for example, that we have in Venice, in Italy. We have the Mose, which is this barrier that stops from the water during high tide floodings to enter into the lagoon and try to protect the city. But I can tell you that the Mose, by half of this century, will be useless because it has not been built to face a larger sea level rise. It has only been built to face a half-meter sea level rise, which we likely reach by the mid to end of this century. And usually when we talk about sea level rise, we forget that we have to add up high tides on top of that. So the higher the sea level is, and the more damage you get from high tide floodings in case of storm surges and extreme weather forecasts. So, okay, so I think that was the main message of these presentations. Thank you very much. If you have any questions. Yep, yep. Perhaps come here. I can't hear you.
Hello,
Hi.
my name is Sebastian. Sorry I got late, but I had a question. What do you think is the main source for the projected uncertainty for 2300? Because I understand this gathers a lot of multi-proxy approaches, etc. But in your opinion, what's the main source for uncertainty when we need to simulate beyond the RCP scenarios?
Yeah, to my opinion, there are two main uncertainties. So you have to think that an ice sheet model needs a climatic boundary to run. Okay, it needs temperature and precipitation and oceanic temperature to then solve the equations. We don't have very good climatic scenarios projected beyond the 21st century because it's very hardly difficult to project the climate state beyond the 21st century. It's already difficult to project it for the end of the 21st century. So that's a major source of uncertainty. The second is the physics itself of the ice sheet model. Right now, those processes of instability I was illustrating before, we think this is working this way, but we are not sure this is working this way because, as I say, those processes they are occurring on several centuries timescale. So we are really unsure of the physics that really trigger exactly the disintegration of ice shelf. We see in geological archives that rapid disintegration occurs, dramatic disintegration occurs. We know the timing basically, but the mechanism within the ice sheets, it's still a bit unknown, and it's highly debated within the community because we don't have the observation to really validate the physics. So that's the main uncertainty right now. And the only observation that we have are paleo data, but they are still, I mean, they are incomplete. I mean, that's only a partial view of the system. The rest we have to somehow make a consensus on what is reasonable or not, and that's the most complicating things. Imagining a physics that you are not able to observe, it's something very difficult. This is where the major uncertainty comes from. But on the fact that Antarctic sectors disintegrate, there is no doubts about that because it happened many times in the past. We clearly see that. So this will definitely happen. The timing, though, is a bit uncertain for us because of that.
Didier Oyon from EDF. Uh, you are mentioning between 40 to 1 meter, I mean, sea level rise. And clearly, do we have some model, I mean, to try to modelize on local what could be the consequences for land use and so on, in order, I mean, to better adapt? Because one of the main topic would be to adapt,
Of
because
course.
obviously it's already done, more or less.
No, so that's a sector that is developing right now because so to let's say downscale all those global projections to local impacts, let's say, you need very high resolution oceanic models and also atmospheric models. So it's coming. I mean, there are many people that are studying the impact of storm surges on the coastline, etc. But you have to think the system as little boxes that incorporate each other's. So when you want to project the climate and the sea level rise at a very local scale, you need the boundary condition around that comes from outside, because of course the climate from a place is derived from the climate of the other places because it's circulation everywhere. So you need a larger box, and you need a larger box, and then a larger box. Okay, so nowadays we are able to do that. However, it's still in development, but we are able to do it. It's just computationally very expensive to do that. And then to have proper simulation at local scale, you need to have proper observation of your bathymetry along the coastline, which is something paradoxically very difficult to retrieve because you need to be at the intertidal range, so where the sea is between the high tide and the low tide, to get the bathymetry right, so you get your projection of storm surges and damage correct. And somehow this is one of the hardest part to retrieve. So for example, the guys from Climate Central have been trying to do that with high resolution coastline and morphology. However, for example, in my place in Northern Adriatic in Trieste, I know that the Climate Central model is not correct because we still lack of high resolution data there. So the first chain is having high resolution coastline data of the morphology, actually above sea level, but a little bit also below sea level. Then you have correct oceanic circulation and atmospheric circulation models that can really reproduce the climate locally. And then you can make proper projections. That's how it is. But it's ongoing. I have many colleagues that do that. But it's not, yeah, it's ongoing. We can do better for sure. So it will develop more.
Hello, nice presentation. Just a question that people a lot of times talk about tipping points, and
Yeah.
your graphs all show very smooth increase over a long time.
Yeah. That's
Yes, yeah. So, what is the implication of tipping points? Are there actual tipping points that are would make that more drastic, or are that kind of incorporated?
no. I mean, so effectively, the melt process or the disintegration process is exponential. So that's why you have this smooth shape of the curve. However, what is important to look when to observe when you look at those graphs is when the rate of sea level rise is definitely changing, because this is where the tipping point is usually. Okay, so of course. Between the two graphs here, for example, there are different tipping points. I mean, the main tipping points on the graph above is about 2150, let's say. Below, it's more close to 2100, 2100. Okay, so well, that's a tipping point. Then the real tipping point in terms of amplitude of sea level rise on the long term, it's after 2 degrees. We see in all ice sheet simulations that after 2 degrees of global warming, there is a huge jump between 2 degrees and 3 degrees, for example. So I've not shown that here, but there is really a huge jump in sea level rise. So the tipping point is around 2 degrees. But we also see that in the paleo data. plus 2 degrees is a tipping point also in past periods that were warmer than today. So it seems to be around that number. Okay. Okay, but so if there are no further questions, thank you very much for attending. And if you are more interested into the impacts and application on coastline, I really invite you to come to tonight events at 6:30 in the Memphis room, because there will be real applications and discussion with Central Central Climate colleagues about that. So thank you very much. Yeah, I can give it to you if you send me your email. Yeah.